Standard quantum mechanics possesses unmatched predictive power, yet the theory contains a persistent structural flaw, the measurement problem. The equations describe a continuously evolving probability cloud that, upon observation, suddenly snaps into a single defined point. But the mathematics provide no specific mechanism for exactly when or why this occurs. Decoherence theory attempts to bridge this gap. It explains how quantum superpositions leak information into the surrounding environment, causing distinct quantum states to entangle with their surroundings and lose their phase coherence. However, while decoherence successfully models this environmental leak, it fails to dictate a physical cutoff. It never specifies the exact moment a single outcome is objectively and irreversibly realized by the particle. Without a strict analytical threshold for collapse, the transition from a reversible quantum state to an irreversible classical reality remains a mathematical ambiguity. Standard theory relies on ad hoc postulates to force the transition, rather than deriving it from the equations themselves. Boundary condition quantum mechanics, or BCQM, is a formal extension to orthodox quantum mechanics that resolves this ambiguity. It achieves this without introducing hidden variables or new stochastic dynamics into the underlying physics. Instead of adding ad hoc measurement rules, BCQM treats collapse strictly as a boundary condition effect. The probability structure evolves normally, but hits a finite temporal limit that forces a discrete outcome. This limit is the coherence horizon, denoted as W. W is defined as the exact analytical threshold where phase covariate system-only recovery becomes impossible. In standard terms, it is the point where a system can no longer be mathematically rolled back to its initial state without external intervention. W functions as an absolute point of no return, grounding the concept of collapse in a calculable physical parameter. We start with the Time Dependent Schrödinger Equation, or TDSE, which is the core formula governing the evolution of quantum states. The TDSE has inherent time symmetry, generating both a retarded solution moving forward and an advanced solution. Standard quantum mechanics explicitly discards the advanced solution as unphysical. BCQM retains both the retarded, or T+, and the advanced, or T-, solutions. Together, they construct a dual-axis probability structure called the Q-wave. This schematic shows the dual axes, T+ and T-, which bound the coherent superposition zone against the collapse horizon W. The T- branch is retained strictly as a mathematical completion for amplitude symmetry, rather than a backward-in-time physical evolution or a mechanism for retrocausality. The Q-wave represented by these axes is an abstract probability scaffold. It is not a physical wave carrying mass or energy, but a mathematical structure defining the limits of coherent superposition. This Q-wave structure undergoes Fourier decomposition into dominant probability paths. These isolated trajectories are referred to as P-waves. This Galton-style lattice shows how these P-waves form a network of specific probability channels. Each branch represents the mutually exclusive outcomes available to the particle as it navigates the abstract Q-wave scaffold. Retaining both branches of the TDSE restores mathematical symmetry to the system. This time-symmetric foundation provides the basis for a fully analytical derivation of quantum probabilities, requiring no new physical dynamics. The theoretical goal of BCQM is to derive the Born rule purely analytically. The Born rule states that probability equals the absolute square of the amplitude, or P equals absolute square of psi. This derivation completely bypasses the need for Gleason's theorem, the standard mathematical proof typically used to justify quantum probability measures. Within the Q-wave framework, the retarded amplitude is mathematically paired with its advanced conjugate. This pairing introduces the parallelogram identity for amplitude probabilities, relying on three consistency requirements: additivity for exclusive alternatives, normalization, and global phase invariance. This identity algebraically forces the probability mapping to be a unique quadratic measure. No other distribution satisfies these constraints. This quadratic measure aligns with the standard ensemble interpretation of orthodox quantum mechanics, where repeated measurements of identically prepared systems yield a predictable statistical distribution. This chart compares a simulated Monte Carlo distribution of discrete P-wave channel landings, marked by the dots, against the analytical incoherent prediction shown by the solid line. The tight alignment confirms the operational validity of the framework. This modulus square weighting arises as an inevitable mathematical consequence of time-symmetric amplitude pairing. To see how this analytical threshold behaves in physical systems, we use the GKLS master equation. The GKLS equation is a mathematical framework that describes the evolution of open quantum systems by accounting for both unitary dynamics and external dissipation. In this context, decoherence is the continuous exponential decay of off-diagonal elements, the mathematical terms representing quantum interference. This decay process begins immediately at t greater than 0. The coherence horizon, W, sits further down the timeline as a hard vertical boundary. The specific mathematical condition for W is the exact moment the optimally recoverable fidelity drops below a defined target threshold, F star. Fidelity measures the similarity between two quantum states. Once it falls below F star, the original state is lost. In the pre-W zone, interference can still be rolled back. If environmental records are erased, the system can be restored to its initial coherent state. In the post-W zone, recovery is physically impossible using phase-covariant, system-only controls. The system lacks the required coherence to reverse the evolution, rendering collapse inevitable. W serves as the strict mathematical boundary where reversibility ends, separating the irreversible event of collapse from the continuous process of decoherence. We can ground this abstract math in physical reality by examining a standard Ramsey sequence. A Ramsey sequence is an experimental method used to measure quantum coherence by subjecting a qubit to specific microwave pulses. We apply this to a system undergoing pure dephasing at a known rate. This chart tracks the visibility decay curve of the Ramsey qubit. Notice the sharp operational knee where the horizon W is crossed, marking an abrupt alteration in the visibility of the quantum state. We see this timeline reflected in modern circuit QED experiments, systems that use superconducting circuits to study quantum electrodynamics. In 2019, Minev and colleagues successfully monitored and reversed quantum jumps mid-flight. Their experiment revealed a roughly 4 microsecond reversal window where a jump could be caught and undone. In the BCQM framework, this window correlates precisely with the pre-horizon zone, providing a real-world lower bound for the value of W. W is a measurable boundary condition already visible in superconducting circuit data. Introducing a hard threshold for collapse requires testing against bipartite entangled systems to ensure it does not violate relativistic causality. Crossing W realizes a joint p-wave channel. This realization is strictly constrained by conserved totals for the entire system, such as total spin or total energy, ensuring the combined properties of the entangled particles remain balanced. BCQM utilizes local completely positive trace preserving, or CPTP, maps. A CPTP map is a mathematical operation that ensures a quantum state remains a valid, normalized density matrix after undergoing an evolution or measurement. Because these maps are local, the marginal state of one subsystem remains entirely unchanged unless classical communication occurs between the measurement sites. By acting locally while enforcing joint conservation, BCQM reproduces verified Bell correlations and Cyrilson bounds, preserving the no-signaling principle and fundamental conservation loss. A theoretical framework is only useful if it makes falsifiable predictions. Standard quantum mechanics assumes that interference visibility is limited exclusively by environmental noise. If you perfectly isolate the system, coherence lasts indefinitely. This chart compares a fully coherent Q-wave interference pattern, marked by the high amplitude peaks, against the baseline of a completely damped incoherent sum of channels, shown by the smooth dashed line. This chart illustrates BCQM's specific prediction, a sharp intrinsic visibility floor. The intermediate dashed wave shows interference is proactively suppressed once path separation exceeds the horizon W. This occurs even at absolute zero, driven purely by the temporal boundary condition rather than external noise. Experimentalists can test this directly. By pushing mid-flight rollback protocols to their extreme limits in isolated environments, researchers can search for this intrinsic floor. If this visibility floor exists, BCQM transforms the mystery of the measurement problem into a quantitative and experimentally testable physical threshold.